Hello students, welcome back to the video on the BJT. So in the last class, we have discussed about what is meant by a bipolar junction transistors. We have discussed what is a transistor and what is the difference between BJT and FET. So in today's class, we will be discussing about the operation of BJT. So we know that bipolar junction transistor will be having current due to two, that is, it is a bipolar. It means that the current is due to both the majority carriers as well as the minority carriers, that is due to electrons and holes. So we will be having two types of transistor. One is called as a PNP transistor and another one is an NPN transistor. So here when we take a PNP transistor, we know that it will be consisting of three regions. One is emitter, base, and collector. And similarly, we will be having three terminal, emitter, base, and collector terminal, and two junctions. One is emitter to base junction, and another one is collector to base junction. So to understand the operation of a BJT, we will consider NPN junction diode. As we have discussed in our first previous module, we know that a PN junction diode can be forward biased or it can be reverse biased. If if the PN junction diode is forward biased, the P terminal of the battery, I mean P terminal of the diode will be connected to the positive terminal of the battery and the N region will be connected to the negative terminal of the battery. In reverse bias, the P region will be connected to the negative terminal and N region will be connected to the positive terminal. Assume that now the diode is reverse biased. When the diode is reverse biased, we know that there will be a depletion region formed. So the depletion region is nothing but the junction of our P and N region. So in reverse biased condition, a diode will be having a very small amount of current, which is called as a reverse saturation current. So the reverse saturated current will be of microamperes and it will be constant for the reverse bias. So the curve, the VA characteristics curve here in the third quadrant, it represents my reverse current. Now assume that I am applying an optical energy. That is, when optical energy or light energy is made to fall on the device, so there will be generation of optical carriers. An EHP will be formed, electron hole pairs will be formed, and because of that, my reverse current increases and my graph gets changed here. So the here the GOP stands for generation rate of due to the optical energy. Now, because of this reverse biased condition, which is exposed to the optical energy, there will be an increase in the current. So, I can control the output current by means of the injected carriers. Now, we assume that we have an hypothetical injection charges injected into the base region. That is, there is some means by which the charge carriers can be induced into the junction. When this is done, then automatically my diode current will be increasing, the reverse current will be increasing. So assume now what we can do is this hypothetical injector or this hole, to inject the hole into this junction, I can have an forward biased PN junction diode. So when I consider a forward biased PN junction diode, we know that there will be a current called as a diffusion current due to the majority carriers. So the majority carrier in the P region is the holes. So the holes will be moving from the P region to the N region. Now, if I try to connect my PN junction back to back with this already existing PN junction, then I will be getting my transistor. So the transistor will be an PNP transistor. So the holes will be injected from the forward biased diode to the center region. From the center region, it will be moving to the third region. So the junction between the center and the third region is called as the collector to base junction. So now because of these two diodes connected back to back, I will be getting NP region. So consider this diagram. So here in this diagram, I can see here I will be having two diodes. One is PN and another one is NP. So both the diodes are connected together with base as a common. That is, the N region is common to both the P regions. Now the first region we will be it is indicated as P plus. So the P plus indicates that it is heavily doped. As we know that this is the source of the charge carriers, then it is indicated as a P plus. Now these holes which is coming from the emitter region will be moving to the end region because this is a forward biased. So we know that during the forward biased condition, the majority carriers will be moving from P to N and N to P due to the diffusion process. So the holes which is there in the P region will be moving to the N region by the diffusion process. So the N and P region, that is the base and the collector region, will be now reverse biased. So we know that here in the reverse biased condition, there will be a minority carrier movement. So because of that, so the holes which is present in the base region due to the drift process will be moving towards the collector region, and also the electrons which is present in the P region will be moving towards the N region, which will be very less when compared to the hole movement. So here finally we can say that the holes are moving from the P plus emitter region to the base region, and from there it is collected by the collector region, which is the P region now. So the output conventional current can be taken as three currents. One is IE, another one is IB and IC. So here to make the transistor to operate, in this case, the emitter to base junction should be forward biased and collector to base junction should be reverse biased. And the current which is flowing is due to the holes only because we know that the electrons which will flow, which is from the collector to the base and from the base to the emitter should be of very less strength. So normally to reduce the recombination and to improve the efficiency of the transistor, our N region will be very lightly doped. So here the VI characteristics if we take, so this is the characteristics of the transistor, output characteristics of the transistor in a common base mode. So here the VBC is nothing but the voltage which is measured between the base and the collector terminal, and IC is the output current, and we can see that IC will be constant for the it will be constant throughout for the different values of VBC, and also we can see that IC will be varied due to the variation in the IA. So here the transistor is said to be a current control device. I have a very small amount of current and that current will be controlling the output current. So the transistor BJT is called as an current control device. Now why is this P plus? So the P plus is nothing but since it is the source of the charge carrier, my P plus will be indicates that it is emitter is heavily doped and it injects the hole into the reverse biased base collector. And for the collector to collect almost all the holes, we need the base to be quite thin and it should be lightly doped. So normally we can say that my base width, that is the width of the base region, we represent always it as W suffix B is to be less than the diffusion length of the hole. That is, diffusion length is nothing but the time for which my hole will be active or the time before which it gets recombined. So the diffusion length should be or the base width should be always, it should be less than the diffusion length of the holes, so that most of the electron holes which is coming into the base region should cross the base region before it gets recombined. So properly biased with BJT on, the voltages are such that my VEB, that is the voltage between my emitter to base junction, should be always greater than 0 to make the junction forward biased, and similarly the VCB, that is a voltage which is applied between the collector and base terminal, should be negative. That is, it should be such that it should reverse bias my collector to base junction, so that if this proper biasing is done, then most of the injected holes will be collected at the collector region, and hence the conventional current relationship can be given as IE is almost is equal to IC, and the large current here when compared to the base. So here to consolidate the video, we can say that In the transistor, we will be having three components, and the biasing is very important here. So that is, the emitter should be heavily doped, collector should be moderately doped, and then the base should be thin, and then it should be also lightly doped. So the next part of this we will be seeing in the next video. Thank you.